we roll, man. Some rock, some win, some 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 win, man.
Hey everyone, my name is Loris Crow and we are executing a Showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime is not just what you're seeing on the live stream, but also the discussions that you can have while watching. And that's why I encourage you to join one of the existing Zig communities that you can find by going to zigland.org. Now, we are at episode number 9. Number 8, sorry. And since I started doing a bit of news when we start the show, the only news that I have for today is something, let's say, just about the show itself. And that's that we set up a newsletter if you're interested. It's a nice way, I think, to get notified about new episodes and learn a bit more about who is going to speak. So learn something about the talks that are going to be there. It should be. I'm still going to use Twitter, but this should also be a nice way of being able to give you more context. Also, I'm gonna put a couple of interesting, useful links for people in newsletter issues. One, for example, is a link to a calendar and also an iCal link that allows you to basically subscribe to the calendar, and so you will get basically Showtime. I'll add events to that calendar so that you get basically in your calendar automatically when the next Showtime airs. You don't have to give me your email necessarily. That's not the point. You can use RSS if you like. There's a link to that, and also the everything that's written in there. If you just care about the content, you can read it online. It's in the archive. If you click the read past issues, you'll be able to see everything. So just choose whatever is the best for you. So with that said, I think we can move to the first talk already. So let me put up the title. Okay. Now. So, kprotty likes birds, makes cute drawings that he occasionally shares with the Discord server, and even has a SoundCloud where he publishes music composed by him. Now, you would expect somebody that has that many artistic interests to not care much about small details in computer science, and yet he has a lot of interest in small details about locking and concurrency, and that's what he's going to talk about today. The title is Build-A-Barging Lock, and Prodi, the stream is yours.
So, yep, talk is about building a barging lock. So, down to the introductions. So, my name is King, or kprotty81works. And I have GitHub where I just post all my unfinished projects. Professionally, I'm a full stack developer, so I do front end, back end, whatever. Just anything with a stack, really. And then for hobby, I just like to optimize stuff. So I mostly do runtime libraries, like anything from hexes to allocators to hash maps, whatever. There are two words there that may have been confusing. So lock and barging. We're going to get to barging later. A lock is effectively, you can think of it conceptually as having ownership of some resource. Like Git is a good example, or a bathroom stall, only one person, ideally only one person can be in there. But like also in Git, only one person can enter the code, and if you have multiple people in there, it can cause some problems, or some corruption, or anything can happen. So a lock is a way to ensure that only one person is, or one thing is updating something at a given time. And so how they're used in programming is through threads. When I say threads, it doesn't have to be OS threads like most people may know. It could be either, it goes by different names like coroutines, fibers, contexts, tasks, what have you. Anything that runs in parallel to another task. So most systems let you write code that technically, or not technically, but conceptually runs in parallel. So when you have things running in parallel, you need to be able to synchronize their memory access. And so that is where atomics come in. So atomics are basically instructions given by the hardware that let you do small little operations that are guaranteed to not be preempted or scheduled in between. So they always either complete or don't complete. And most times they just complete. So the top is what they do algorithmically, and then the bottom is some examples of x86 code. So using these atomics, you can build higher level synchronization primitives out of them. And that is where the thread lock comes in. So this is a basic lock for an OS thread. So you try to swap or atomically swap a value to true. And if it returns false, as you can see from here, it returns an old value. But if it returns false, that means the new value must be true. And you were the first thread to change it to true. So you return, meaning that you own the lock. To release ownership of the lock, then you set this value back to false. So then another thread can swap it to true and get ownership. It's like a cycle that you spin until you finally are able to grab the lock, if that makes sense. So now it's time for a demo. So I have a branch. I'll link the code after the talk, but it basically is used to benchmark locks. So you use it by running your script here, and it lets you customize how much time is spent inside the lock, how much time is spent outside the lock, and the different thread levels for contention. So it's like good to control all these different attributes to see which situations your lock runs best. So times I put here for like 10 nanoseconds, so 100 side, and then 10 to 500. They're like, it's a randomized range, so it tries to be as realistic as possible. So here is our test and set lock, which is the spin lock we had earlier. Don't worry, I'll explain what the results mean, but well, let's just start with the headers of them. So each time it runs at a different thread level. So how many threads are actually running lock operations, and then the settings we passed in earlier. So this is the name of the lock, and pthread mutex is the one that comes with the system. So it's going to be our baseline for what is fast, what isn't, and we're trying to get better compared to. So the test and set lock is the spin lock that I explained earlier, and average locks is how many lock operations all threads running formed per second. So this is basically the throughput. I'll explain what that is later as well. But when you hear performance, you generally think of throughput. So the higher this number, the better. Standard deviation is the variance. So how different amounts of lock operations that each thread complete. So if one thread did 100 locks and another thread did 10 locks, the variance would be higher. And when the variance is higher, it means that one thread is monopolizing all the lock operations. So it's probably should avoid that. So lower is better in here. So as you can see, there's little contention. The spin lock is really fast, at least 2 times faster than the blocking lock provided by the system. Keep in mind that these results are, this is probably a disclaimer I should have done earlier, but these results are local to my machine, to my OS, my CPU combination, and whatever else is running. So if you try to replicate on your system, you might have different results. Something might be faster, some things might not be. But basically a way to show how these core algorithms perform in general. So it gets actually really fast, low amounts of contention. But as we get into the amount of threads per core, because I'm running this on a Ryzen 5 2600, 12 CPU logical threads. As we get to that limit, it starts to grade really, really fast. And that is because every thread that has lock has to spin until it relinquishes its thread quota so another thread can run. So threads that don't have the lock but aren't scheduled, the spin, and the one that needs to release the lock might have to be scheduled after or before the spinning ones. So it has to wait for all the threads that are running to spin and realize that they can't be scheduled anymore, and then get back in the run queue, wait for all of them to come, and then that decreases the amount of time spent actually doing lock operations. That's where the throughput decreases. So we need to find a way to mitigate that. In order to improve that, we need to understand how the cache works. So this is a fairly simplified version of the cache, where each core talks to each, you would call it a layered cache object, and each cache object talks to the RAM. So anytime a core wishes to load or read or write a memory, it has to go through the cache. So let's say I wanted to load this memory. Cache already has it, so it clearly returns it. This is a pretty quick operation. But if it wants to update a memory, it has to make this new value aware of all the other caches. And that requires invalidating the memory. And to invalidate means that all the other caches have to go back to RAM to see the new updated value. So if another thread tries to load X after the invalidation, so we'll all the way back to RAM, then cache the value and return it back. So this operation in particular is what makes atomics slow when under contention, because multiple threads storing to the same memory address makes everyone else try to read from memory again. This is the saying that you hear that mutexes are slow. They're not really slow, but mutex contention, where everything is refreshing and validating, is actually what makes it slow. So let's design a lock to try and mitigate that. This is basically the same as the test and set lock, but instead of immediately invalidating, because remember the swap from earlier, there's a load then a store. Always stores and invalidates. But we only invalidate if load says that the lock is unlocked. So just keep looking at our local cache until someone says lock is unlocked, and then we all try to race to grab it again. It avoids a constant invalidation and only invalidates and the lock is released. So theoretically, this should be better on cache. So let's see if that's actually the case. So, as you can see here, run the test again. But this is one of the cases where, for my configuration specifically, it's not really much faster than the constant invalidation. One reason for this could be just the microcode for how AMD implements it. Another is that cache coherency, or the synchronization of the caches, is actually faster on modern hardware, but I can't really tell. So this is just one of the cases where the theoretical doesn't really match to the practical for this specific instance. But regardless of that, you can notice that at the higher contention levels, the standard deviation is slightly better. I don't have an explanation for that either, because I think this one is random, because the results for standard deviation vary randomly based on how much time is spent in the lock and off the lock, especially for spin locks. So over throughput, which was how many locks there is, and then latency, which is how long it takes for a given lock operation to complete. That was a standard deviation from earlier. But a lower standard deviation, the better the latency. So latency is important where you have one thread that needs to complete something after it locks. It doesn't want to hold or wait on a lock forever while another thread keeps trying to grab it. That would be what we call fairness. And fairness is another property of locks that you try to code for, or one that you balance out because there's no perfect lock balance. You have to generally favor one or the other. Barging, as the title says, is when the lock is unfair. So the thread that acquires it releases it, sees that other threads are still trying to acquire, it can barge in front of them and acquire it again. That it can do more lock operations if it's faster than them. There's a benefit of increasing throughput, but as you can see, other threads have to wait longer, so it's really bad for tail latency. Let's try experimenting with this. The way fairness is implemented is through basically making a queue of threads who gets the lock. And I explained the benefits of it, the drawbacks of it, and we're about to see it in action with ticket locks. So this is generally the first type of fair lock that comes to mind when you think of fair mutexes. It was made famous by the Linux kernel. They use it in some places, at least as far as I can tell, but switch to another lock that I'll cover soon. The core algorithm is that get a ticket by incrementing a counter, wait for the owner of the ticket to become the one you incremented. So you can imagine if you have one thread with no contention, increment it, you get back to 0 ticket. The owner is already 0, and you continue. Then when you release the lock, you make the owner 1, and then you acquire it again, you increment it to 1. So it just falls through. If there's 2 threads, you increment it, maybe 1 already, so you have to wait for the owner to become 1. The owner becomes 1 when the ticket 0 incremented on the release. So it's like a release back into acquire. That's how it forms a queue of threads based on numerically increasing tickets. So let's see how that performs in the face of implementations. You can see that throughput is okay at 2 threads. Still okay at 6 threads, but as the contention level increases, the throughput drops dramatically. But to counteract that, the standard deviation remains really small. So this lock is generally fairer than most locks that we're testing at the moment. Just when it means that the just don't have to wait as long to get a lock and don't have to wait for someone who's it. So it's all fine, but I'm trying to build barging locks here, so we really care about throughput. But since we're still curious and like optimizing, we can try and get fairness to the absolute minimum just for fun. That's where we use MCS locks. So this is, I mentioned earlier that Linux kernel uses spin locks, but they moved to MCS because it has a few pretty good properties. So how it works is that it creates a linked list of threads. And so each thread that releases the lock picks up the next thread to it. This does is that release no longer invalidates the cache of all the other threads looking at it, like in ticket lock, but instead invalidates the cache of the specific thread that's trying to wake up. So you have all these threads spinning on their own memory, so they don't have to go into RAM until it wakes it up. This has the same like cache efficient effects as the test and set, as we explained earlier. And so this should theoretically perform better than spin lock or the ticket lock. because of the direct cache notification. So, and for the record, the MCS lock implemented here actually blocks the thread until instead of spinning. As you can see, even already at lower contention levels, the standard deviation is really low, so it's more fair than a ticket lock is. So it remains and continues to be that fair, even when contention levels are high. If you have some job that's latency sensitive, this would be the ideal lock to go for. But if you have something you care about throughput, it's not that great compared to others. If we have the best of both worlds, so people thought about it, and there's like a general class of locks called hybrid or adaptive locking. So these work is that they try to acquire it by invalidating a cache line really quickly. This is good for if there's no other waiters, so they can just quickly grab the lock and move on instead of having to do the other logic. If it is already locked, then it tries to spin if there's no waiters already. If there are waiters, then it just goes to sleep like normal. So this has the benefit of the fast acquire of spin locks when it's uncontended, has the also added benefit that it doesn't degrade that fast as spin locks do when multiple threads come in. And it's mostly popular. pthread mutex uses it, Parking Lot uses this scheme, and the one that we're going to demo actually based off of the lock found in the Golang task scheduler. So this lock has been tested multiple times. It has the same adaptive approach as earlier, but it's Linux only. As we can see, the throughput is competitive with the spin locks, even at lower thread levels. It remains even faster than spin locks at higher thread levels, also keeping a fairly low standard deviation. This throughput that it displays, it consistently has this throughput better, regardless of how many threads we throw at it. So this is like the best of both worlds. This is generally the locks that are found in the wild, and why using a blocking lock doesn't have to be slower than spin lock. In most cases, it's probably better to go for the blocking lock. You get all the benefits, but with most of the drawbacks. And I say most because faster ways to do spin locks, of course. So the ones I've showed so far are mostly just the naive implementations. There's tons of optimizations. Don't actually use these spin locks, please. They're bad. One of the optimizations you can do is back off fielding. The idea is to, every time you fail to acquire a lock, a little bit longer and a little bit longer. What this does is make like an interleaving of how many threads are trying to acquire a lock at the same time to reduce contention. So it's mostly a throughput optimization, meaning that it lets other threads acquire the lock faster since there's less contention. It has the unfortunate property that you have to wait longer and longer, which is really bad for latency. It also uses scheduled, which has its own issues of undefined or unspecified behavior. But effectively, it yields the current thread, the next thread on the run queue of the current core. Makes sense. So why that's important? Why that's important is that it makes it so that for high contention levels, threads just yield back to the next one that needs to release a lock instead of having to spin for its whole quota. And you can see through this optimization, it's some pretty interesting numbers out of it. So here we have our threads going along, being fast, some of them slow properties, and then there's our back off lock, which has incredible throughput. but okay is standard deviation. But as you can see, throughput remains high. So does the standard deviation, and that continues to climb even at higher thread counts. So it's consistently faster than everything else, but trades that off for every thread not able to hold the lock. So it's basically just optimizing the lock for a given thread, whoever's fastest, which is what you want in a barging lock, but not what you want in general purpose. So again, spin locks are not general purpose. Don't use them as such. But the right optimizations, they can achieve really, really fast throughputs if you know your scheduling environment, if you know how to implement them correctly. So, is barging locks. I intentionally left a few things out because they're really big topics that I don't want to cover in this talk. Atomic memory ordering. So how do locks keep memory safe? Because atomics only apply to the single variables, so you need ways to apply it to whatever it's trying to protect. There's also eventual fairness. It's the concept of try to barge first, but if there's a lock that's been waiting too long, form a queue. So it's like a kind of the hybrid approach, but for solving barging instead of solving scaling. False sharing is the idea that updates to or invalidates from a cache line or a memory region can affect their memory regions that you don't want it to. You want them to be in cache, but the atomic accesses are making them having to refetch. And then direct yielding is yielding from one thread exactly to another to avoid all the run queue stuff that the scheduler does. So these are all interesting topics, but I left them out because you can do it and research on your own. I'm not interested in it that way. So finally, here are the references. The first link is the link to the GitHub for all the source code in this presentation as a benchmark. And also includes some other links here, like I got the cache visualization from this presentation. Going inspired the hybrid lock. This whole lock thing started with parking lot and wondering if I can make that faster. It's been my big inspiration there. This article has some interesting thoughts on how the spin locks degrade and the different levels of concurrency going bad. So it's a really interesting read. All of these interesting reads. So go check them out. And that is how you build a barging lock.
Wow. Thank you very much, King. Let me switch to the Q&A view. Okay. Whoa. That was a nice presentation, man. Yeah, applause. Please, slaps in chat. That was so. Man, so just give a bit of context to the viewers. So we've been going back and forth about having Protty do a presentation for a while now. I think we started talking about it even before the summer break, and yeah, it was a while now, and that was awesome. That was really awesome on many levels. Like the drawings are amazing, King. You always say they're not much, but I think they were pretty good. Yeah. By the way, there's a bunch of slaps in chat. Like I don't know if you have Twitch open. You shouldn't. But
no, I don't.
Well, in any case, you'll be able to check them out later in the VOD. So yeah, that was amazing. Okay, thank you. Okay, enough slaps now. Questions. And while people think of questions to ask you, let me start with the usual warm-up questions. So let's start by asking you, how did you get into Zig? How did you discover it? I think you were mentioning during the pre-show that you started with version 0.4. So I don't know. What's the context?
So I saw Andrew's video on Road to Zig 1.0, like a long time ago. didn't really get interested in from that point, but after playing around and again dissatisfied with all the weird C stuff, and then dissatisfied with Rust not letting me do what I want, and plus being just the weirder C, stumbled on Zig. It seemed like it was focused on resource efficiency, which is what I really like, or really try to strive for when I write code. So it aligned with a lot of stuff. Got in the community, Discord, interested in a standard library. The mutex was my first PR, and then it all like snowballed from there.
Okay, sorry, I was just letting people know in Discord that you don't need a Twitch account if you want to ask questions. Road 1.0 radicalized me as well, says Man Knight. Yeah. So if you are in IRC or in the Discord server, please just write your question there. Maybe tag me so that it's easier for me to notice that, and I'll be happy to relay your question to King. So no worries. Okay, so that's what brought you here. Yeah, we got radicalized by Andrew. Okay, second question. Do you want me to share your SoundCloud to the people? That's usually... No?
Okay. That's full of all the weird random stuff that I just happened to generate when I was in a preteen. So interested in that, sure. But it's not really something generally shareable.
Okay. Then if you want a link to it, you'll have to ask King personally. By the way, how would you like, if anybody has other questions that they want to ask you, maybe because they're seeing this as a recording on YouTube, how would you want them to contact you?
That's my Discord. Put it here.
Let me bring that full. Let me pull this up. Oh no, your face is covering. Add a couple of new lines. Thank you. Okay, Roddy. 1246. Okay.
Any other questions?
Okay, so we have a question. Yeah, you explained nicely why you want both low latency and high throughput. Are there other dimensions that you might want to optimize for?
Those are the main two. The other one is the size of the mutex. That's not really one considered by many, but it's kind of important, especially if you want to embed your mutex in like their different structures. So one of the good implementations of this is WebKit's parking lot. What they do is have the mutex state inside just a single byte. There's actually 2 bits. And what they do is map the address of it to the shared list or queue of threads, similar to how Futex works internally. So you can have mutexes that are the size of like a byte, and they fit in small JS objects. And so that's one of the optimizations you might consider when trying to make mutexes. Besides that, cancellation is also a big one. Like being able to say, I want to lock only for 3 seconds and then give up. That requires a completely different architecture than merging. So you have to be able to support adding a thread in and then removing a thread out at any point in time, and all the interleavings between all of that. So different ways you can optimize mutex, different features you can add of it, but barging is kind of the most common.
Okay, we have another question from Discord. So the question for you is, can you do a presentation about hazard pointers? Hazard. Oh.
Hazard pointers, that's more of memory reclamation, and I guess it is memory synchronization. It's just not locking. I can do that for a future talk, but cover atomic memory orderings first before I do memory reclamation. Too deep into that yet.
Okay. Oh, there's another question. This one is from Andrew. Any tips or suggestions or general guidance for Zig standard library, for the event loop in the Zig standard library?
Reduce contention. Now everything is going through, I think, the same equal queue, which basically has a spin lock underneath. Every time you submit a task from any thread, it has to lock the spin lock, and you saw how well that scales. So reducing contention by either doing work stealing or basically distributing tasks to threads so they don't have to look to other threads as often. That's basically how Zap got fast, or how Golang gets fast.
Okay. Let's see. Let's give maybe a few more seconds if there's any other question. Let me double check Discord and IRC. I think we are good. King, do you have anything else that you want to say to the public before we move to the break?
You can check out the source code for all of this. I really like this mutex benchmark. I haven't found any other tool that does it, so I like to play around with locks, go there, do unlocking algorithms, see how well they perform. Always submit a PR because I'd like to see them too.
By the way, if you can share with me some of the links later, I'll be able to put them in the YouTube description for the recording of this presentation, which I think would be nice.
Alrighty.
Yep. Okay. Cool. Thank you very much, King. That was an awesome presentation as usual. Your art is pretty nice. I think everybody loved it. So thank you, and I'm really looking forward to have you do a second talk. Then we can chat about this later. Okay. So now we are moving to the 10-minute break, after which we're going to have another nice talk about rewriting C++ code to Zig. So see you soon. Okay, we're ready for the second talk. So, Guillaume is a research engineer who decided a while ago to learn Zig. Like many others in our circle, he has a troubled past where he was forced to program in C++, and in his case, that happened at a company that has "Don't be evil" as its tagline, ironically enough. Nowadays, he mostly programs in Python, but I guess he still has a need for speed, which brings us to today's talk. The title is Rewriting an LLP Tool from C++ to Zig. Guillaume, the stream is yours.
Hi, everyone. So I wanted to first introduce what this tool is about and how did it go with the rewrite, some benchmark number, and then I'm going to talk a bit about like a Python wrapper I made for it, and we proceed with some conclusion. So first, so the algorithm FastBPR, it's called bytes per encoding, and it has been made in like 2015. It's been used in a lot of natural language processing papers and research, mostly working with neural networks. And I wanted to, so the original there's in the C++ implementation, which are already pretty fast. The name, it's called FastBPA because the first paper back in 2015 published a Python implementation, which was quite slow. And I wanted to learn Zig. And I thought it would be a good fit because there's like 500 lines of code, so it was a small project. And I was impressed by the Road to 1.0 talk from Andrew, and I wanted to check like this claim that Zig can be faster than C. So first, like what's byte pair encoding? And so when you work with text, the first thing you want to do is like split it into words, mostly because words are actually convey a lot of information, and like learning a neural network for any task would be far easier if you start from words instead of starting from characters or bytes. The problem, of course, is like word isn't a well-defined concept. It's like language specific. Like for instance, isn't in English is often considered by most tokenizer as one word. But if you look in French, you have this word kill is mean it is mostly considered as two words, so you can't use the single quotes as a word separator. It's not always the case. It's not in English, but it is in French. And also some languages don't really have words. I can mention like Turkish or Chinese. Like in Turkish, it's very common to slap words together and make very long words that you won't never find in a dictionary, but they will appear in when people speak between them. So of course, like the tradition for this tool is to have regex tokenizer, and so for each language you will have a lot of specific rules. Some language use dots, for example, in dates, or they use dots in currency. So you have to handle them specifically for each language. So of course, it assumes that you know the language of your text, which is not always the case when you're working with text that come from the web. And also it creates another problem, is that you have a very large vocabulary. And that's particularly an issue for neural networks and language models. Language model is a kind of machine learning algorithm that tries to predict the next word in a sentence. And if you have a vocabulary of 1 million different words, you have to generate a probability over 1 million words. So first, it's costly to compute, and it's also hard to learn a good distribution. And even if you have 1 million words of vocabulary, you will always find words that are outside of your vocabulary, that your model doesn't know how to handle them. and it would be like proper names, person names, small cities. It will also be, also mentioned before, like for Turkish, you will have people making new words, or so on. And even if you have note out of vocabulary, you will still have some words which are really rare and that your model has only seen like once or twice in your full training data set, and it doesn't really have a good representation, a good idea of what to do with them. So byte pair encoding solution was to split the text in frequent chunks of characters. And so I put an example. I'm eating some apples. Might get tokenized like that. So you have and eating will probably be split into two parts. One is the common word eats, and the ing is also very frequent in English. So you hope that your byte pair encoding algorithm will keep it as one chunk. And it's a good compromise between linguistics, so it's not like what a linguist would call correct speed. The algorithm is also pretty fast. And also you can have a good control on your vocabulary size. And like for something like under 500,000, you will have a good coverage for English. And if you go up to 200,000, you can cover like all languages at once. I wanted to say that this algorithm is not really state of the art anymore. If you want to use something like this right now, I would recommend rather sentence piece, but I still choose byte pair encoding because first the code was quite straightforward. And I also knew the person who wrote the fast byte pair encoding implementation in C++. So I figured out it would be easier for me if I had questions. And the main issue with byte pair encoding, I mentioned in the blog post, is that it's using word frequency, and some characters, like the dot, you will have some artifacts, because since dot is a very frequent character, it will always, every letter that is followed by a dot will be a frequent pattern, and you will have a lot of this pattern with a dot at the end, which is not really something that you really want. And the underlying theoretical flaw is that byte pair encoding is only using row counts of patterns instead of a point where there's mutual information. So I can come back on this if you're interested. So the algorithm is as follows. At training time, you use some very basic tokenization. So you split on all spaces, new lines, things like that. And you count each n-grams, each pattern, how often it happens. So I'm talking about all the pattern of letters. And at inference time, you will start, first you reuse the same basic tokenization on spaces, and you start by splitting all the characters into the different group, and then you try to merge them, and you start by always merging the one with the highest score, which is the score is like how many times you saw this pattern in the training corpus. And you merge like this. First, here in the example, I have eating, all letters are spread out, and you start by merging E and A, and then maybe the N and G and ing. The only order is the scores of those. So the algorithm is like mostly linear. You have a small quadratic component in the length of your words, but you can assume this is relatively small. And okay. Now I'm gonna move on like what I did to rewrite in Zig. And first there was some issues with the C++ implementation. So C++ was like pretty, I would call it idiomatic, but it made an heavy use of a standard library and vectors appending two vectors and string concatenation. So there was a lot of vector creation. So every time you would create this list of token, every new step you will create a new vector with a new list of groups. And also you will also concatenate the characters one by one to store them in the token list. Yeah, so the thing is, like, if my goal was not necessarily to make it, yeah, my goal was not to make the tool faster, but when I rewrote it in Zig, you realize quickly that allocating a Zig is a bit painful. So you try to think about twice when you do it. And what I did, like for the vectors, instead of allocating a new vector each time, I just have two vectors and then I swap them at every round. I have always like the current state and I have the new states. Small optimization like that. And also the strings, they are not concatenated, but since I'm using slices, concatenating two slices is like free. I just, recompute the end of the slice and I have a new slice. And also one of the things you have to do when you write Zig code and you try to pre-allocate the memory is you need to think about like pathological edge case. And in my case, like I have a buffer that stores the current word I'm processing. And I decided that it cannot be greater than 4K bytes. And then if it's greater than that, I can just, currently I'm just keeping it, but I could just, split it in some arbitrary size chunk. It's not really an issue in any case. I probably can just replace it also by a node token or something like that. So that's the kind of thing that if you feed this kind of word to the original implementation, your model will take a very long time. Typically, if you give the Chinese text, which doesn't have any spaces inside it, you will just have your code going very, very slow because you ate like a pathologic edge case that nobody had ever thought about. While in the Zing implementation, you kind of have to think about those, and you will have something which is not great, but at least your process will exit in a reasonable time. Okay, so now moving on to the benchmark. So I only evaluated the parts that apply. By parent coding, I didn't evaluate the part that trains. I did some benchmark about the training too. It was similar. So both two implementations are pretty close together. So I'm just gonna focus on the apply parts. So I used an extract of French Wikipedia, and all the implementations, they produce the exact same files at the end. And for C++, there was two implementation. One that takes the whole file in memory and treats it with 4 threads. And the other one read from standard inputs and process line one by one in a single thread and write the result to standard outputs. And this is the only thing I implemented in Zig. First, because I still don't know yet how to make multi-threading works in C++, in Zig, but also because most of the time I don't have my corpus lying on one file. Like I have a text file which is 4 terabytes long and it's compressed. I don't want to load it in memory, and also don't want it to store it uncompressed on my disk. So I don't want to map it or something. Anyway, let's move on to the benchmark results. So basically, like the C++ implementation is 3 times slower than the Zig one. And I think it's important because currently in natural language processing, most of the time people will do all the pre-processing offline before training because it takes time and but in turn you lose reproducibility, and also, because typically sometimes people will distribute data sets that already applies their own preprocessing, their own bypass encoding, and then at some point someone lost the model and you cannot ever redo it, or you cannot reuse the original text. Anyway, so yeah, the Zig implementation is faster, and but that's not really surprising considering I had to change the memory allocation, and now let's talk about Python wrapper. As Christophe said, I work a lot with Python, and a lot of neural networks these days are trained with Python, at least logic that loads the data and describes the neural network is in Python, and then Python call CUDA kernels that are very optimized codes. And so, it's very common to use Python bindings. There's different ways of doing Python bindings. You have Cython, which is like a Python-like language, but that can be compiled. But it's not really Python because Python is highly dynamic, so you have some kind of subsets of Python. You have also PyBind11, which is a C++ library that lets you manipulate Python objects. So you can take, so you literally have a strict called PyObject, and you can set fields, and so you can, it's basically you have to learn a lot of things, and you can manipulate Python directly, which can help, but it also means that you generally can't leverage C++ libraries because they're not meant to work with Python object anyway. And then, of course, you have a CFFI for Python, and you have two ways of calling C function. There's CFFI and C-types. I use the second one, C-types. I think it's a bit more modern. So the benchmark code is doing only the processing in Zig. Everything else, like reading the code file, is made in Python. The idea is I wanted to benchmark a case where where you have the maximum flexibility, because you can also call a function in Zig that load the file, read it, and write the result somewhere else. But when you want, but that's not the typical use case of people using Python. If people are using Python, it's because they want more control over what's happening. Maybe they want to add more processing steps and so on. As it happens, like most Python wrapper are about the same performance of the original code. Cython is a bit faster than C++. I don't know why, and C-types is a slightly bit slower, but as I will explain later, I thought it would be I thought the difference would be bigger. So coming back a bit to, so I did some profiling of the two Python wrappers. So the first one, I'm not going to spend much time on it because I think it's pretty messed up. Flame graph, when you have something compiled with O3, it's really a mess. The code stack is really not preserved. All I can say is apparently it spends a lot of the find method of that dictionary, which is at the core of the algorithm. And they also spend a lot of time doing pushback. And I think this is because of them not pre-allocating vectors And the Zig flame graph is much cleaner. It's really more easy to understand what's going on. You have actually a big part, which is like this part. Answer capacity exact is called like 25% the time, as this is only called during loading of the model. So I can probably be more aggressive here by pre-allocating more memory right out of the box, or yeah. And also, yeah, there's like 40%, which is copying back the results from Zig to Python, which is here in this part of the flank graph, if I remember correctly. Oh no, it's here. Yeah, I think it's here. And also you have spike by C functor pointer call, which is like 6%. So the two, and so you have like 20% overhead when coding Python. That's why I was expecting the overall code to be like 20% slower, but it's actually about the same speed. So I guess there's something else. Sorry. Something else going on. I think probably, I don't know, maybe some part of the Python code is actually very fast. I don't know, maybe it's reading files from Python, which can be explained if they have, I don't know, bigger buffers, things like that. I haven't dug in this part. Yeah, so we are reaching to the conclusion, and I wanted to make a few comments about the Zig Python interface. And the thing is, I have to expose a C function in my Zig code, so it looks like something like this, and it's not really nice Zig. You can see, like, I have to send take a pointer and a length. And similarly, on the Python side, I take the sentence as bytes, and also have to declare the type of my function here. It also makes for like a function which is not really Python friendly, because I also have to send the sentence and its length, and also have to pass a buffer. So yeah, so I think this part is a bit repetitive. I don't know how we can make it more easier, either with better. I was wondering, maybe I could ask the compiler to generate for me a Python files, which could expose this kind of function instead of exposing these ones. Yeah, but I haven't proceeded into that. I don't know if a lot of people are working with Python and Zig. I'd be interested to know if there is a niche. Yeah, so as I said, there's some to-dos I want to do. Yeah, I'd like to improve my code with adding multi-threading, with using async await. I'm not exactly sure what would be the right level of synchronization between my different async await procedure. So the pain points I had with Zig at first, obviously, that I need to think about memory allocation all the time. And yes, thing that I never realized before I need to think about it, like resolving a file path. You have a path to a file name, and you want to know the full path to be able to actually run the file, and just for that you need to allocate memory. And so I mean, yeah, some part of your code, what you would like to not pass the allocator, you still have to. Also, I was not used to this level of error handling. I think it's very interesting. But it's, yeah, in a way, it also remind me a bit of the old Java days where you had to expose all the errors you can return in the function signature. Yeah, also I was surprised to find that even in standard libraries, you have a lot of private members and functions. Typically, yeah, so I have a hash map, and I want to print all, so the key is a string and the value is a score. I'd like to print them all sorted by score. And basically, I would like to call array.sort on the underlying array used by the hash map, but I can't because it's private. Yeah, and so I need to copy it, which is a bit weird for me. And so, yeah, so I'm not sure why there's so many private members in the function into standard library. Coming from Python, it's a bit surprising. Yeah, and also for a language that claims to be like C, it's also a bit surprising for me. But anyway, as also mentioned, the Zig Python interface is a bit cumbersome, a bit verbose, I would say, even though it seems to be reasonably fast. Yeah. But I just want to say I still had a good time writing Zig. I found it refreshing. I also think that the Zig source code is pretty great. Standard library, it's better, way better than the automatically generated documentation. And also it's a good source if you want to learn the language. And yeah, that's all for me. Thanks for listening. And I'll be happy to take some questions.
Okay, awesome. Let's switch to the Q&A view. So while people start thinking about questions, and by the way, like before, if you have any question and you are not in Twitch chat, but you are in Discord or IRC, feel free to send your questions there. I'm opening up all the relative windows, so I won't miss your question. Okay, so Guillaume, in the meantime, let me start by asking you let's say the standard question. When and how did you discover Zig?
I think it was in March during the lockdown. Yeah, I don't. Yeah, or maybe no. I think no. I think I heard about it earlier. Yeah. So at some point, someone was asking me. Yeah, there was some interest group. Some of my colleagues wanted to learn more about C++, and I was like, I really wanted to say to them like, don't learn more about C++. Just learn a good language and add don't anything to propose them that would be better. And so I started hunting around the web, and I first found J, which doesn't exist actually. And I finally heard about Zig. I think it was around January, and yeah, and then I found yeah, I was looking for a first project, and I decided and starting during the lockdown.
I see. So you started very recently. That's good to know.
It's very recent.
Okay, so another quick question. Maybe I am misremembering, so feel free to correct me. But I think I remember a while ago I was also experimenting with. I was taking a look at calling Zig from other programming languages, and I remember also trying with Python. I think I remember CFFI also having a static way of loading, basically CABI binaries. Yeah. I might be misremembering though.
I didn't look a lot into it, into a CFFI. Just, yeah. Okay. So maybe I'm wrong.
I see. Well, the reason why I'm bringing up CFFI, I think your point about having the the integration code be automatically generated, that sounds perfectly reasonable, and I think it's something that that, by the way, would be, I think, easy to implement as a userland library. Like, I don't think you would even need anything special from the compiler.
No.
Generally speaking. But that said, the reason I brought up CFFI is because, like, at least in my case, I had an easier time with that, because CFFI loads, like, it can parse header files. So I remember being able to use the automatically generated header file by Zig to get function definitions.
Okay.
Yeah.
I didn't thought about that. I remember seeing something about the header file, but I wasn't sure how that would apply to Zig.
To be honest,
Zig has
Sorry?
Zig has a translate to C somewhere function?
Not exactly, but it does have a. So when you compile as a dynamic library, your Zig code, you also get. Maybe now it's broken, so I'm not aware of the current state of things. But the Zig compiler can generate header files whenever you export something with the CABI, and so that came in handy, at least when I was experimenting. But that said, maybe you didn't care much because, as you mentioned about the speed, like I never really cared about how fast the integration was, and when I tried, I just wanted to make it work. So that's why I settled with CFFI. let me
So
see.
I look into it.
Let me see.
I look into it.
Okay, let me see if there's questions. So there's one in Discord. Wait, that's in French. Oh my god, man! Fan code. I am the one that has to read those to the speaker. Why are you making it harder for me? You have to be subjected
I
to my
don't
French.
have.
No worries, no worries. I want to do this. I want to try this.
Okay. I also have Discord. I can.
Okay. Quel est ton prochain project en Zig?
Oh yeah. So what's my next project in Zig? I don't know. Maybe like a mentioned sentence piece. Maybe I will look into that. It's a bit more. Sentence piece is also making use of protobuffer. So maybe I look into generating protobuffer API for Zig or something similar. Yeah, I don't know, but I also want, the very next thing I really want to do is this multiprocessing, because I really want to understand how it works. I think a way it seems cool from what I heard about it, because I haven't really practiced it. So I want to do that first.
Okay. Let me see other questions. This one is from Andrew. Can you share more about your NLP project? What are you working on in terms of like big picture?
So I'm a Facebook research, and I work on. Yeah, so basically we train several. I don't know if you heard about GPT-2, GPT-3. So we're also doing things which are similar. So that's mean training big language model on a hundred of gigabytes of text called from the web. These models are then used for classification tasks. So abuse detection, hate speech detection, and more recently, I'm more focused on content retrieval. So you have a piece of text, and I want to, like a Facebook post, and I want to find other Facebook posts that says similar things. Or it can also work with newspaper articles. And it's better if it can work across several languages. Yeah.
Okay. Yeah, there's another question by Dirk Code. Would you use Zig at your day job?
So I don't choose Zig at my day job. I'm considering it. For now, it seems a bit hard to promote it in my day job. Just like typically, I wanted to recompile my code before the presentation. And I don't know why, I also upgraded the Zig compiler. And of course, there was a lot of warnings. So I think for now, it's a bit unstable to use at my day job. And also, like typically for this project, the speed is not really that important, because we are talking about models that use hundreds of GPU hours to run. So spending 3 more times for the pre-processing is not that a problem, because it's only CPU. CPU is cheap in comparison. So I don't really have a good case right now. But if I was, unless I'm starting a new project which I need to write in a low-level language, I don't think I will use Zig at work. But if I do, I look into Zig.
Okay, well, I can say that for the people watching, if you are interested in trying to introduce Zig at your day job, I think as Guillaume said, it's a bit early for Zig to be used, I think, in production, generally speaking. But if you want like a couple of life hacks, one is to wait for us to get to the self-hosted compiler and wait for us to be to a point where it's easier to ensure that a feature doesn't break. And at that point, maybe you won't stay on the unstable branch, right? Because then you will get breaking changes. Like I think for Guillaume, what got him was a a change in the hash map implementation, right?
Yeah.
While if you stay on a tag release, then that won't happen. And at the same time, though, the idea is that once we get there, we'll be able to provide like stability patches also for certain features that we want to keep stable. The second life hack that I can say is that, for example, again, it's not really, I don't know if it's used in production right now, to be honest, because I don't work there anymore. But at least in my case, what I did was I implemented a module for Redis that we were using at our job. This is not as during my work at Redis Lab. This is before, so it was actually used to do stuff, not just by Redis Labs itself, but it was on my previous job. And what I did was it was a very small library, very small in scope. And the thing is, it was a piece of software that you could consider basically mostly done. It works. It's not going to break. The scope is not going to change. And once you compile it, it's compiled. So as long as you don't change our CPU architecture, you're done. You have the compile executable, and you don't have to worry about much else. Anyway.
I think for my case, like FastBP, encoding is still used by some teams, and if I could give them a binary that just works, I think they'll take it. The only thing is, like, for now, I didn't implement the multi-thread thing, and that means that for some use case, it will be slower than the original one. And I'd like to be on par on every axis before pushing something new.
Yeah, makes sense. So let's see. Just checking the discussion on Discord, but no new questions. Okay, so I think we got most of the questions. I think I have one last question for you. So, for the people watching, Guillaume also published a blog post about his experience doing this work with Zig. And if you're interested, I think you can find the link in a few places. Did you link to it in the repository?
Yes, in the repository, and it's also, I put it in Zig showcase in the Discord at some point, but you probably have to scroll back up a lot to find it.
Yeah, I also added it to the newsletter. So if you caught the last newsletter, or if you want to check the archives, you will find the link. And so I read it, and in there you were pointing out that one of the limitations that that BP has is that it's based on frequencies rather than on mutual information. Would you be able to like explain this a little bit to the viewers?
What I can say is, like, so for BPO, what you count is you look at all times you have a group W1 of characters that appear next to W2. And so, so this gives you the score. So it's just the number of times you see it.
Yes.
Sorry. And what I want to use information, you would normalize by the number of times you see each characters independently. All right. Yeah. So first, and we are gonna pass that into probabilities. And what does that mean is, this is the probability of the two of them appearing together. And this is the probability of the two of them appearing together, even if they are totally independent events. So in my example with the dot can appear next to almost any letters, but it's not as much, because the dot is something that often comes after some specific word. But most of the case, most often it's just because the word is actually very present. So if W2 is a dot, you will have this probability, which is pretty high, and so the score for this PMI will be low.
Mm-hmm.
Whereas for the Viper, for just the count will be still be very high.
Okay, that makes perfect sense. So if people are interested more on these, I don't know, computer science, statistics, like less just low-level software engineering part, take a look at his post. I actually, at his write-up, I enjoyed it a lot.
Okay, thanks. It's
yeah.
actually the first time I write a blog post, and I already spent way too much time on it, but it's really not as good as I want. But yeah.
It's always like that. Well, it's just a matter of practice. Okay, so Guillaume, is there anything else that you want to say before we move to the end of the show?
No, I'm good. Thank you for having me. I think it was a fun experience. The more I'm hanging out with the community, the more I like it. So maybe you have not done seeing me.
Okay. Well, it's been a pleasure. I'm looking forward to hearing again from you, both in a Showtime talk or even just a link on the Showcase Discord channel. By the way, if you are interested in doing stuff like you mentioned earlier, a library for protocol buffers, I think probably there will be other people in the community interested in this stuff. So consider also telling about people early. Like don't just put the link of the completed library in Showcase. You might find somebody that wants to help you. Okay, that was great. Thank you very much.
Thanks. Bye.
Bye. Okay, and we are at the end of today's Showtime. So let's see, final words for today's episode. Well, of course, subscribe to the newsletter. If you have anything interesting to say that is Zig related, please do apply to speak, or shoot me an email, send me a direct message on Discord or something like that. Let me know. I think everybody is really looking forward to hear more stories about Zig from people that are using Zig. And that I think is all. So next episode is gonna be next Saturday, so Saturday 19th of September at 2 p.m. Central European time, so much earlier. It's like, I think, 6 hours earlier than today. For people in California, that might be a bit early, but everybody, it has to be early or late for somebody, right? And that's just how it goes. So thank you very much, and see you next time.
This is how we